Hello and welcome to section 3.3. This section in your book covers Bronsted-Lowry acidity as well as how to compare the strengths of two acids from a quantitative perspective. So first we have to um, consider a reaction that looks like this. Looking at this reaction, some acid, HA, plus water is in equilibrium to give us A minus plus H3O plus. It's about as easy as it gets from a general chemistry perspective. Also, we can measure the amount of A minus and H3O plus that are generated here using the equilibrium constant equation or the KEQ equation, which is shown here. The equilibrium constant K is equal to the concentration of H3O plus times the concentration of A minus over the concentration of HA that is left plus the concentration of H2O. And you might remember that broadly, this can be thought of as products, the concentration of the products over the concentration of the reactants. We're not going to go into solving these exactly right now, but what you need to know is that is the equilibrium equation for uh, any reaction, any acid-base reaction. KEQ here is in general for any reaction, but for any acid-base reaction, we can instead use the Ka constant, which is the acid dissociation constant, which is simply equal to KEQ times the concentration of H2O. And the reason why we use the concentration of H2O here is because the concentration of H2O is mostly constant because it is the solvent used in reaction. And being the solvent, it doesn't really change it doesn't really change very much during the course of the reaction. So that means that we can then simplify the Ka equation to simply being the concentration of the H3O plus and A minus that are formed, because they should be equal, all over the concentration of undissociated HA. Okay, so at least this gives us a new equation to think about here, and Ka is actually usually pretty small. It's usually so small that it's difficult to really describe in normal numbers. This would be very many decimal points, especially for weak acids, like we're going to deal with in this class. So instead of using a normal linear scale, we're going to use a logarithmic scale, which means that we're going to take the negative log of Ka. And if we do that, we're going to end up getting the pKa. You might remember that the negative log of the concentration of protons in a solution is equal to the pH, right? We learned that as well. Here we're going to talk more about pKa. That is the strength of an acid to dissociate whenever it is in a solution or dissolved in some solvent. And table 3.1 in your book gives some really nice beginning pKa values. As you can see here, so you can have some pretty common acids that we'll deal with in this class. You can see like this sulfuric acid has a pKa of -9. It's very strong. A protonated oxygen also is a pretty strong acid, -7. And as you go up in number, that means more positive, you're going to have a weaker and weaker acid. So this means the lower number, the most negative pKa, indicates the strongest acid and the weakest base. Where as you go higher in number, such as with just a regular CH, CH is a very weak acid, but whenever you have the conjugate base of this very weak acid, the negatively charged carbon here is the strongest base in the table. So I encourage each of you to have a look at table, what is this, 3.1, and familiarize yourself with basic functional groups and their pKa's, because we will be using these over and over in this year of organic chemistry that you're taking. Okay. So one other thing that you should know is that we can directly compare two pKa values to tell what the strongest acid is. This is kind of what we were talking about a second ago in the table. So if we were to take, for instance, these two molecules and compare the acidity of the red proton, we can compare their pKa. Here, water has a pKa equal to around 15.7. At least that's what your book says and what some other values I have say. And what I'm going to do is actually change what this specific alcohol is. We're going to do it in bond line notation here. There we are. So that's now ethanol. Okay. Good. And its pKa is equal to around 16. So here, water is very much more slightly acidic than is the ethanol because its pKa is lower. So when you have a pKa that is lower for one acid than another, then you have a stronger acid. And there is a very helpful table of pKa values that you can find on the internet simply by Googling Evans pKa table. It's a very good pKa table that has pKa's of like so many functional groups. So for instance, we were looking at water, there's 15.7, and I drew in ethanol, which is similar to this isopropanol, and it has a pKa of around 16. So you can see there's carboxylic acids. There's all the strong acids here, such as H2SO4, which I read in your book, HCl and HBr, as well as the protonated version of water, and several more complicated functional groups. So just so you know, this is a resource you can use, and I'll be also adding this to the course shell in Canvas for your use as well. Okay, so what we'll be doing a lot in this class is not just comparing the acidity of these two, looking at the values in the table. We'll be in future lectures figuring out how to actually qualitatively determine the pKa values of two chemicals and which of those protons in the two chemicals should be the most acidic. The reason why we do this is because there are so many types of chemicals and molecules that we can encounter in organic chemistry. It doesn't make sense to have to look in a table each time. What would make more sense is that if we knew a series of rules that we could follow that would allow us to correctly guess which proton would be the most acidic in each case. So that's what we'll learn, and we'll learn this by kind of simulating this acid dissociation event in real time like this. So we would say this water is in an equilibrium with its conjugate base, as shown here. And the same thing for this ethanol. as shown here. This has been section 3.3.